Let's start out with a little story. The game of chess, so goes the story, was invented thousands of years ago in India, and the inventor of the game, when he presented the rules to the emperor, so impressed the emperor that he was offered any reward that he chose. And he decided to use this particular riddle. He said he'd like a single grain of rice for the first square on his chessboard, and then 2 grains for the next square, 4 for the next, 8 for the next, and so on, doubling every time, 16, 32, 64. Now, a grain of rice is not particularly big, and even 64 grains of rice makes a pretty measly mouthful. So the emperor thought he was doing pretty well, getting off fairly cheaply. Turns out, if you double enough times, you get some really, really big numbers. I'd encourage you to have a go. Start with a number on the calculator and double it. Press times 2 equals, and you'll find that pretty quickly you get up to some pretty big numbers. The 8th square will contain the number 1 doubled 7 times, so it actually comes out as 128. On the first 8 squares altogether, well, if you add them all up, it can get a bit tedious, but you should get the number 255. And you might notice something about the number 255. When you work out how many grains of rice there be on the 9th square, we get an answer of 256. And in fact, that pattern continues for any number within this sequence. If you add up all of the first, say, 16 squares of the chessboard, the total will be 1 less than the 17th square. This is a pretty powerful idea. It means no matter how far up the chessboard you've managed to go, filling the squares with the required number of grains of rice, to fill just one more square will take more rice than you have so far used altogether on all the previous squares. You might think you're getting pretty close if you got all the way up to square number 60, but you have square number 61 to go, and 62, and 63, and 64, which means you are only about 6% of the way through, because the 61st square will contain as much rice as you've already got on the board, plus 1 extra grain. And then if you thought that was a lot, well, the 62nd square will need everything that you've already got, which is all the first 60 squares plus the 61st square plus another 1. Numbers get big fast. This is the total number of grains of rice you would have on the entire chessboard. And if you're wondering how big of a number that is, well, it's more than the entire global rice harvest. Not just thousands of years ago when the game was invented, but in today's standards. It's more than the amount of rice the entire world consumes. And in fact, not just in a year, but in 500 years. That's the sort of number we're talking about. Nobody, as far as we know, has ever been rich enough to be able to buy this much rice, even if it was sold at ordinary prices. Okay, what we're looking at here are geometric series. We're dealing with sequences of numbers which increase by a common proportion. This should look familiar to you. We've been looking at interest rates and how if you multiply by 1.12 many times, you're doing a 12% increase over and over again. The numbers will get bigger and bigger and bigger at an ever increasing rate. It's called exponential growth, and it's very closely tied in with what we see with interest rates and with investments. You may already have done some work with arithmetic series. You might have called them linear series. They are sets of numbers that go up in regular steps through adding. You add 3 over and over again. With a geometric series, the commonality between one term and the next is the ratio between them. If you divide one number by the previous one, you will get the same answer every time. So the sequence 1, 5, 25, 125, and so on is a geometric series with common ratio 5. Each of these, A, B, C, and D, are examples of geometric series. So look closely and see if you can identify that common feature that they have. We're looking for the common ratio. The first one should look familiar. That's what we were dealing with when we were adding up the first few squares of the chessboard. 1, 2, 4, 8, 16, 32, 64. Now the common ratio is not asking you to add them all up, we'll get to that. The common ratio is just asking you what do you multiply by each time to get from one term to the next. Hopefully you've spotted for the first one, we're doubling every time. But for B, to go from 8 to 40, you have to multiply by 5. From 40 to 200, also multiply by 5. The key thing that this type of series has in common with all other geometric series, you will be multiplying by the same thing every time. That thing doesn't necessarily have to be positive. In most of the examples we'll see, it is going to be positive. We'll be talking about things that are either increasing as time goes by or possibly decreasing as time goes by. But we know that both of those things can be thought of in terms of multiplying, either by a number bigger than 1 or a number smaller than 1. This last one is a good example. If we multiply by a half, each new term is half the size of the one before. And they shrink pretty fast. In fact, they shrink at a comparable rate to the rate that the other sequences grow. C is a bit of a strange one because the size of the numbers gets bigger and bigger every time. Each new number is 10 times the size of the previous one, but the sign of the numbers alternates. Every time you multiply by -10, you change the sign of your number. Now we come to the terminology that goes along with geometric series. In order to be able to effectively describe them, work with them, calculate things about them, we need to have a consistent set of values that we recognize and refer to. We start with A, which is the first term. Good way to remember this is that A is the first letter in the alphabet. So when we talk about A or we refer to A in a formula, we're talking about the value of the very first term or the very first number in the sequence or series. If your series goes 5, 10, 20, 40, then the first term is 5. R is the common ratio, we've talked about that already. That's the number you're multiplying by. If you go 5, 10, 20, 40, you're multiplying by 2 every time. N represents the number of terms in the series that you're interested in. Or sometimes we think of N as being the position of the term that you're interested in. So if I'm only looking at 5, 10, 20, 40, perhaps I'm thinking of N as being 4, because I'm interested in the fourth term, 40, or maybe the total of the first 4 terms, 5 add 10, add 20, add 40. But you can think of a geometric series as going on forever, so it can be helpful to be able to specify how far along the series we're interested in doing calculations for. And that's where the next two come in. UN represents the nth term. In other words, the term in the sequence, the number in the sequence, which is n places along. In the sequence 5, 10, 20, 40, the number 40 is U4. It is the fourth term, so we refer to it as U4. And Sn corresponds to the total, the sum of the first n terms. So S4 will be 5, add 10, add 20, add 40. S infinity is a bit of a strange one. That's an infinity symbol there. When it makes sense, and only when it makes sense, we can think about adding all of the terms. In other words, like we said, the series can be thought of as going on forever. There's no point at which you can no longer multiply by 5, say, or by a half. So in some cases we might find that no matter how many terms you add, you never get beyond a certain limit. You get closer and closer to a number, but you never get beyond it. In those cases, we can calculate the value of that number, and we can think of S infinity as being the sum of all the terms in the series. We will talk more about that later, because that's the bit that's the most mind-bending about this whole topic. So, I would recommend you pause at this point and try to calculate the values of A, R, U5 and S5 for this geometric series. Let's see how you got on. The first term is 1. That's the very first number that appears in the series. And the common ratio is 2 because you multiply by 2 every time. If you're trying to make sense of a series, the first thing we often look at is whether you add the same thing between one term and the next. If you try doing that here, you'll find that what you're adding is 1 and then 2 and then 4 and then 8. What you end up with is another geometric series. Turns out the most effective way to think about these is in terms of what you multiply, and that's what gives you the clue that you're dealing with a geometric series. If you end up multiplying by the same thing every time, that thing is called r, and we call it the common ratio, and in this case it's 2. The fifth term is 16, and the sum of the first 5 terms is 31. Now we're going to get onto the formulae that we can use to deal with these. And if you look carefully at what I've got written on the top, this is what every geometric series ever looks like. The first term is a, and every time you go from one term to the next, you multiply by r. So to get to term number 2, you have to multiply by r once. To get to the third term, u3, you have to multiply by r twice. Because to get to the first term, you don't need to multiply by r at all. You're already at the first term, a. If you want to get to term number 4, you have to multiply by r 3 times. So have a think about what the formula might be for the nth term. We should get a times r to the n minus 1. In other words, to get to term number 10, you need to start at the first term, a, and then move 9 places along, multiplied by the common ratio 9 times. See if you can apply this formula to find the 10th term of each of these sequences. For the first one, a is 1, r is 2, so we can do 1 times 2 to the power of 9. Remember, the power is always n minus 1. So if we want the 10th term, then we need to raise the common ratio to the power of 9. For the next one, we start at 8, but we're multiplying by 5 every time. The next one, we start at 6, and we multiply by negative 10 every time. You've got to make sure the negative 10 goes in brackets if you're going to do this on the calculator. But if you haven't in this case, you might not have noticed the problem. If you try negative 10 to the power of 10, you should get a positive number. If you don't put the negative 10 in brackets, the calculator will think you want to do 10 to the power of 10 and then put the minus in front. So watch out for those. For the last one, the first term is 100, and every time you multiply by a half. So we have 100 times a half to the power of 9. For those of you who are curious, I'm going to work through here how you can generate the formula. But you need to be aware that if this goes a bit over your head, not to worry. This is not necessary. You don't need to be able to construct this formula for yourselves. What you do need to be able to do is use it. It will be provided in the formula book. You need to be able to apply it to different situations. But it's quite a nice proof, so I want to go through it. In general, the sum of the first n terms will start at a, and it will add up all of the terms up to the term un, which remember is ar to the n minus 1. Now if we multiply both sides of that equation by r, what you end up with is a bunch of terms which look very familiar. Instead of a at the beginning, we have ar, which appears in the second position in the line above. Ar squared also appears in the line above. And in fact, almost every term in the green equation appears in the blue equation. And almost every term in the blue equation appears in the green equation. That almost is the bit we care about. Nearly everything cancels out when we do this next clever step, because those two pieces that are now circled in purple, they're exactly the same. And if I were to subtract the right-hand side of one of the equations from the right-hand side of the other one, then all of that stuff in purple disappears. It doesn't matter how big n is, it's the same stuff. So if we subtract the bottom equation from the top equation, we get this. On the left, Sn minus r times Sn, and on the right, a minus ar to the n. When we factorize and simplify, we end up with a formula for the sum of the first n terms. So this is our formula, and this is the formula you need to be able to recognize. It'll be in your formula sheet, and you need to be able to use it. Let's have a go with a few of these. These are the geometric series that you saw at the beginning. Apply the formula to find the sum of the first 7 terms for A, and then the sum of the first 5 terms for the other 3. And if you want to check your answers, you can go through the process of adding up the terms and seeing if they match. But try using the formula and see if you can put it into the calculator efficiently and accurately enough to get the right answers. we should have 127, 6,248, 54,546, and 193.75. Now that last one should be interesting to us. We've added up the first 5 terms, and we've found that we've still not quite got to 200. You could try doing the sum of the first 10 terms, or even the sum of the first 20 terms, and see if you can get to the point where it gets beyond 200. Spoiler alert, you probably won't. Now this is where we start talking a bit about the sum to infinity. In other words, the sum of all of the terms. If you imagine walking 1 meter across a 2 meter room, and then for your next step you walk half a meter. So now you're only half a meter from the end. And then for your next step you walk a quarter of a meter. So now you've gone in total 1 3/4, 1.75 meters, and you're only a quarter of a meter from the end. And then you walk 1/8 of a meter, and now you're 1/8 of a meter from the end. And every time you do a step, you go half of the remaining distance. Now if you continue to do this, because every single step only gets you halfway to the end, you will never get to the end. If you ever get to the end, you have to ask the question, well, where were you before that a half step to the end will get you all the way to the end? Well, it doesn't make much sense. But there is a really useful idea behind this. If you can grasp in your head the idea of doing something an unlimited number of times, then we can use that and generate for ourselves a formula that fits, that makes sense of it all. We're going to talk a bit more about that in the next PowerPoint, but this is just to give you some idea. If you're looking at the squares in this diagram, you can look at all of them, or you can just look at the ones on the bottom. You could find the sum of the first 5 terms, or the sum of the first 10 terms, or the sum of the first 100,000 terms, and you'll probably start to notice something happens as you put the formula into the calculator. The calculator will give up at a certain level of precision, and it'll just say, well, it's probably approximately such and such. Have a look at the numbers and see if you can predict what's happening. And then when we get to the sum to infinity, hopefully that will make sense to you. Now I'm going to go through a couple of examples. We're going to look at net present value, and we'll use geometric series to interpret the problem. Andrew has just retired and received the first of his pension payments. He's going to get £5,000 at the beginning of every year for the remainder of his life. So every year another 5,000. Now immediately, hopefully, you can see why this is different to an ordinary net present value problem. It doesn't say you get £5,000 now and then another one in a year's time, another one in a year's time, and then you're done. It's for the rest of his life. Well, we can work it out for a particular number, and we'll see what that ends up looking like. A discount rate of 5%, and we're interested in the net present value of the first 10 payments. Well, that's a lot of payments to put in a table. It's going to be quite tedious. There's going to be a 5,000 from the money he gets straight away, and then there'll be 5,000 divided by 1.05 for the next one, and then 5,000 divided by 1.05 squared for the next one. And if you find yourself writing something repetitive, then you're probably not using the most efficient method. We gradually realize there's a pattern going on here, and it's going to keep going until we get to the final payment, which will happen in 10 years' time, which in present value terms is worth 5,000 divided by 1.05 to the power 10. Now look closely at all of those numbers we want to add together. What we're looking at is a geometric series. Every new term has been multiplied by the same thing. To get from one term to the next, we've multiplied by a common ratio of 1 over 1.05. Now you might be thinking, no, we've not multiplied, we've divided. We had 5,000, then 5,000 divided by 1.05, then 5,000 divided by 1.05 divided by 1.05. And you're right, but dividing by 1.05 is the same as multiplying by the reciprocal of 1.05, multiplying by 1 over 1.05, which is at about 0.9 something, but it's easier to write it as 1 over 1.05 because it's a slightly awkward decimal. Once you've figured out what your first term is and what your common ratio is, we can apply our formula. It looks a bit messy, but it's one line, put in a calculator, get an answer. So the net present value of those 10 payments of 5,000 a year over the next 10 years is actually approximately 40,000. That's a useful figure to be able to get. And it's also really helpful to see how we can do that for 10 terms without it needing to be a case of calculating every single one of them. We could ask a similar question for 30 years, and instead of it taking 3 times as long, it will take a similar amount of time. The only difference will be, instead of having a power of 10 in the formula, you're going to replace it with a power of 30. And then if you want to ask the question, how long if he lived for 100 years, in theory, who knows what might happen. If he lives for 100 years, well, we'll replace that 10 with a 100. And in each case, you can calculate a value. What if he lives forever? Well, I'm skeptical of the advances of science that might be necessary for that particular eventuality, but it's a useful idea mathematically because it puts a definite upper bound on the amount of money that that pension is worth. Even if he lives for an incredibly long length of time, well, there is a limit to how much the pension is worth, and we're going to talk about how you can calculate that in the next presentation. For now, S30, hopefully you've got an answer of about 80,000. So live for 10 years, it's worth 40,000. You live for 30 years, it's only worth 80,000, about twice as much. That's because most of the payments will be happening quite a long time in the future. Of course, what this means is, in 30 years' time, if he's still getting 5,000 a year, that 5,000 probably isn't going to be worth a huge amount to him because of inflation, but that's a whole other issue. 100 years, S100, comes out to about 100,000. So even though he's been paid 5,000 100 times, which should be 500,000, because most of those payments were a long way in the future, they are worth less and less. Each new payment that we're talking about, the one that happens in 100 years' time, is 500 divided by 1.05 to the power of 100. That's a very small number. And if you could work out the sum to infinity, the formula is not that complicated, and we'll talk about it later. Turns out the sum to infinity is 105,000. It is impossible for him to live long enough for the payment that he's being offered to be worth more than 105,000. Mathematically speaking, there is no way, even if he lived for thousands of years, millions of years, even if this was some kind of trust fund which was guaranteeing a payout of £5,000 a year forever, all they would need to do to ensure that there was enough money now to pay for that payment in perpetuity forever would be to invest £105,000 at a 5% interest rate. Every year they could pull out 5,000 and give it to a deserving scholar who gets a scholarship award. And then during the year they'd accrue interest at 5%, they could pay out another 5,000. Again, 5% interest, pay out another 5,000. If you think about it, it makes perfect sense. If you've got £105,000 in the bank right now, and you immediately pay someone £5,000, then you have £100,000 in the bank. Well, if you wait a year, and you get a 5% interest increase, your 100,000 becomes 105,000. Then you can afford to give away 5,000, and you still have 100,000 left. So you're basically living off the interest. You're never going to run out of money at this rate. Now, if you started with 104,200, then each time you earned interest, it would be not quite enough to cover the previous £5,000 payment, and therefore you would gradually use up your money. But it would take you 100 years to get to the point where you have none left. If you start with 105,000, you will always have 100,000 after you give away the 5,000. You'll always have 105,000 after you get your interest paid. Here's another example. This one involves effective rate of interest. So there's a few things going on in this one. A regular savings account is one that generally banks will be able to offer a preferential interest rate for because they strictly limit how much money you can invest into it. So if you want to put away £5,000 and you see a bank account is offering 6% interest, which they were not too long ago for some regular savings accounts, well, you can't really get 6% on your £5,000 because there will be a limit to how much you can put into the account at any one time. In this particular example, we have a maximum monthly deposit of £200 and 2.4% is the nominal annual interest rate, and it's compounded monthly. That means you can put in £200 right now, but then you have to wait a month before you can put in the next £200, and the interest will only be paid on the money that's in the bank. Well, we start like we would normally start with effective rate of interest. Because it's compounded monthly, I'm going to break the nominal annual interest rate into 12 equal pieces. 2.4% per year ends up being 0.2% per month. In other words, the multiplier is 1.002. Now, the deposit that you put in the bank straight away will earn interest for all 12 months. Your second deposit will earn interest for 11 months because you have to wait a month before you put it in, and so on and so forth. So when you get to your 12th payment, it's only in the bank for a month, and so it only makes that 0.2% once. This is what it looks like. I've done this out in one long line this time. 200 times 1.002 to the power 12 is how much money you make based on the very first deposit that you make. The second deposit that happens 1 month in will make you 0.2% interest 11 times, and then so on and so forth until you get to the 12th deposit, which is only in there for a month and therefore only makes 0.2% interest once. Now again, this is a geometric series. There's something here that I want to mention. I didn't want to throw it in the last slide in case it confused people, but we are safe to read this geometric series either forwards or backwards. If we consider that final term as the first term in the series, then things get a lot easier. We don't need to think about 1 over 1.002 as being our common ratio. We can think about 1.002 being our common ratio. As we move from right to left, we are multiplying by 1.002. That's why the power of 11 turns into power of 12 when you go in this direction. Doesn't matter which way you do it, as long as you're consistent and you remember which term means what. Now we've got a formula for S12, the sum of the first 12 terms. We substitute the numbers in, and we have fewer awkward fractions in this one, and we end up with a number £2,431.43. Then we should always check to see that it's sensible. Now the method for this in this case is going to involve looking back at how much money you actually put into the bank. We can have a monthly deposit of 200, and because it's a monthly deposit of 200 and we're interested in how much we have after a year, we know that the actual money we pay into the account is going to be 12 lots of 200. £2,400 goes in, and we end up with £2,431.43. In other words, we've earned interest of £31.43. Now, is that reasonable? Is that what we would expect? Well, here's how we need to make sense of it. Think about how it's different to just putting in 2,400 and expecting 2.4%. There are two things that make it different. One of them is that we're compounding monthly, but as we saw when we looked at the effective rate of interest, although that does increase the amount of money you get slightly, it's only ever very slight. In this case, I've calculated it just for the sake of argument. The effective rate of interest for monthly compounding at 2.4% is 2.426%, so still pretty similar. It's slightly better, but not a huge amount. That's not going to have the biggest impact here. The biggest impact of a regular savings account is that most of your deposits are only earning interest for a short length of time. Yeah, you put 200 in at the beginning of the year, that's been earning interest all year. So you've effectively got 2.426% on your first £200 investment. But the final £200 investment you put in, that's only been earning interest for a month. It's only got you about 0.2% interest. And all the ones in between will get you different amounts of interest, but about half of them happened after 6 months had gone by. So really, a better approximation than just what's 2,400 with a 2.4% increase, which will give you 2,457. That's a bit higher than what we've got. And the reason for that is that most of your payments didn't earn interest for most of the year. Half of them got more than 6 months of interest and the other half less. If you use this general rule of thumb here and just halve your interest rate when you see a regular savings account, that'll give you a better idea about what's going on. £2,428.80 is what you get if you just say, let's go with 1.2%. They say 2.4%, but it's a regular savings account, which means, roughly speaking, half your payments will only be earning interest for less than half a year. The other half will be earning interest more, but roughly speaking, we'll treat that 2.4% as if it's actually a 1.2%, and that'll give you a pretty good approximation. That's a really quick and easy calculation to do, and then you can directly compare it and you can see whether your answer was likely to be correct. So now I want to clarify exactly what's happening with S infinity. We can look in detail at the Sn formula, and if we try replacing n with infinity, and for the purposes of this, we're going to think about infinity just as being a really big number. Well, you can test this out with some different numbers yourself. If you make r equal to something like 0.9, you can try 0.9 to the power of 100, or to the power of 1,000, or to the power of 1,000,000,000. And what you should find is 0.9 to the power of a large number becomes a very, very small number. In fact, if you could raise it to the power of a number as large as you like, then you could make the answer as small as you like. And we could say that raising it to the power of infinity is effectively making it as small as possible, which means 0. So 1 minus r to the infinity becomes 1 minus 0, which is just 1. So we have a times 1. And that's why the formula reduces down to a over 1 minus r. However, we made an important assumption here. We assumed that we were dealing with the sorted number that when you multiply it by itself lots of times, the result gets smaller and smaller. That works with numbers like 0.9. It works with negative numbers if they're small enough in size, like minus 1/2 or minus 0.9, but it doesn't work if the number is 1 or minus 1 or bigger in size, like a 2 or minus 1.5. It's not going to work. You can try it. If you try 1.1 to the power of 1,000, even though 1.1 is a fairly small number, it's still pretty close to 1. If you multiply it by itself enough times, it's just going to get bigger and bigger and bigger. So the only time this calculation makes any sense is when the common ratio, r, is smaller in size than 1. The notation for this involves putting vertical lines either side of r. This is another way of saying the size of r. So ignore the negative sign if there is one, and check that the size of your number is less than 1. In other words, it should be 0 point something if you work it out as a decimal. Let's see how this works. For each of these series, we can determine whether or not they converge, and if they do converge, in other words, there is a value when you try adding up all of them, it doesn't just give you something nonsensical, but there really is a sensible value, then what would that value be? For the first one, the first term is 0.3, but the thing we really care about is the common ratio. We're multiplying by 0.1 every time. And since we're multiplying by 0.1 and 0.1 is smaller than 1, we're safe. We can do 0.3 divided by 1 minus 0.1, and it comes out as exactly a third. If you think about this, it shouldn't surprise you. If you try adding up those first 4 terms, you get 0.3333. If you tried adding an unlimited number of them, you'd get 0.3 recurring. In other words, 0 point and then 3's forever. Well, that's exactly what this infinite series means. It's 0 point and then 3's forever. That's not just similar to a third. In some sense, it is the same as a third. You can't find a number bigger than one but smaller than the other one. It doesn't work because those two things are the same. For B, bit of a sneaky one, you're multiplying by minus 1 every time. But because minus 1 is not smaller in size than 1, its size is 1, we can't get a sensible answer for S infinity. It's interesting to try. You get a weird looking answer if you try putting it in, but it's not really a sensible answer for this sort. If you think about what happens as you go on further and further, you don't get closer and closer to 3 or to minus 3 or to 1.5 or whatever else. You just keep oscillating back and forth. You either have a total of 3 or you have a total of 0, and you never get closer and closer to anything, unlike A. Now C is multiplying by 0.95 every time. In other words, we've got a 5% decrease for each term. And although they still seem fairly big, the first 4 terms are not much smaller than the first one, but it still converges. It takes a bit longer to get to its overall total, so the total is 2,000, but because the common ratio is smaller in size than 1, it will converge and we can calculate S infinity, the sum of all of the terms. What this means is you could quite safely promise somebody £100 this week and 5% less the week after and 5% less the week after and 5% less the week after forever, and you would only ever need to spend £2,000 as a sort of maximum. Doesn't matter how many weeks you spend, the maximum you're ever going to need to give them is £2,000. For the next one, we're multiplying by minus 0.2. Well, the size of the common ratio is less than 1, so we can safely apply the formula. Just be careful with your negatives. 1 take away minus 0.2 is 1.2. So this comes out as 833 and a third. And the last one, these numbers seem to be getting bigger, but only a little bit bigger. Well, even though it's only a little bit bigger, it's still enough to break the rule. The common ratio is bigger than 1, so we can't apply this rule. Now, here's the sort of example that you might have to come across. How much do I need to set aside in a long-term 2% interest savings account in order to provide an annual return of £1,000 indefinitely? That word indefinitely is your clue that we're going to be dealing with something where instead of getting the sum of the first 10 terms or even the first 100 terms, we're trying to think about the sum of all of the terms. What if we could carry on paying out £1,000 every year forever? Well, the way this works is we start by writing down how much money we would need right now. The best way to think of this is in terms of net present value. So the first £1,000 we have to pay out is worth £1,000. The next £1,000 I have to pay out doesn't have to be paid out for a year, so I've got a year to save. In other words, at 2% interest, I need to have £1,000 after a year. How much would I need to save now to make £1,000 available in 1 year's time? And then the second year, we'd need to pay at the end of the second year, I suppose. So the third payment, we would need to be able to pay £1,000, but we've got 2 years worth of interest to earn in order to pay that £1,000. Now, it may not look like we have a common ratio that is small enough here because there's a 1.02 going on, but if you notice, it's 1,000 divided by 1.02. And if you work out 1 over 1.02, you'll find that it really is less than 1. We're dividing by something bigger than 1, which is equivalent to multiplying by something less than 1. So we can use this formula. The first term is 1,000, the common ratio is 1 over 1.02. And when we substitute it in, we get a sensible looking answer. £51,000. I could pay you 1,000 from that right now, and I'd be left with 50,000. When I collect my 2% interest, which will happen during the coming year, it'll go back up to £51,000. Then I can safely pay you the £1,000 again, and then wait a year for it to increase back to £51,000. So you can see how this works. It makes perfect logical sense. It doesn't matter that infinity is a weird idea and there's some strange concepts going on with infinite sums. What matters here is we've found a way to calculate how much I would need to invest in order to consistently and reliably, for as long as I like, produce an outcome of 1,000. This is how you live off the interest of something for more than just the next 10 years or for your lifetime, but just in general. This is how you fund things if they need to be funded long term.